Today we'll be talking about section 2.3, characterizations of invertible matrices. Specifically, we'll be looking at the invertible matrix theorem. The invertible matrix theorem ties together a lot of the concepts that we've been talking about all term into one central location. So let's take a look at what this is. So the invertible matrix theorem is specifically looking at a square matrix A. So A is going to be an n by n matrix. So if A is squared, then the following statements are equivalent. So what this means is we have a list of 12 properties, and either all 12 of them are true or all 12 of them are false. So this is all tied together with this concept of an invertible matrix, which we talked about in the last video. If a matrix is invertible, then all 11 of these other things are also true. If the matrix is not invertible, then all 11 of these other things are also false. Let's take a look at each one of these. So property A says that A is an invertible matrix. We talked about in the last video where if A is an invertible matrix, how do we find its inverse? We find its inverse by augmenting it with the identity matrix and then row reducing. And then if after we row reduce, there's an I, the identity matrix on the left-hand side, then the right-hand side is A inverse. What this specifically tells us here is that in order for A to be invertible, A has to be row equivalent to the identity matrix. That's directly coming from our algorithm. So if A is an invertible matrix, then it's definitely going to be row equivalent to the identity. So this means that property A really means the same thing as property B. If A is row equivalent to the identity matrix, then in the identity matrix we have ones in every single row and column. And there are n rows and columns, that means we have n pivot positions. So if A is row equivalent to the identity matrix, that's the exact same thing as saying we have n pivot positions. So B is really saying the same thing as property C. Now, if we have n pivot positions, that means we don't have any free variables because we only have n columns. So if we have no free variables, that means we only have the trivial solution in the homogeneous system. So C is really saying the same thing as D. Let me actually rearrange this. Let's put D underneath so I have more room. All right, so C is saying the same exact thing as D. All right. Now, if we have only the trivial solution, that's literally the definition of the columns being a linearly independent set. Remember how we talked about if we have a free variable, then our columns are linearly dependent. If we don't have a free variable, if we only have the trivial solution, then the columns are linearly independent. So D is really saying the same thing as E. All right. Now, property F is saying the linear transformation that takes a vector x to the vector ax is 1-to-1. We talked about in our video on section 1.9 that that's going to mean the same thing as being a linearly independent set, as the columns being a linearly independent set. So if you'll remember, 1-to-1 means x can, every output has only one input mapped to it. So in particular, we can't have infinitely many things mapped to ax, right? And so that's another way of saying our columns are linearly independent. So property E is the same thing as property F. If that one feels a little shaky, go back and rewatch the video on section 1.9. All right, property G is the equation ax equals b has at least one solution for every b in Rn. Now, when does ax equal b have a solution for every single b in Rn? That happens when we have a pivot position in every single row, because that means we can't ever have a row that looks like zeros all on the left-hand side of the augment and something non-zero on the other. We can't ever have this because if we have a pivot in every row, we don't have this row of zeros, so we can never have an inconsistent system. Well, we have n pivot positions, that's what property C says, and there are n rows, which means that we have a pivot position in every row, so property C is saying the same exact thing as property G. All right. Property H says the columns of A span Rn. Well, if we have a solution for every single B in Rn, that's literally by definition the same thing as spanning Rn. So property G is saying the same exact thing as property H. All right. The linear transformation X that sends X to AX is onto. That's the same thing as saying everything in Rn gets hit. Everything in Rn has a solution. So properties H and I are also saying the exact same thing. All right, property J and K, let me skip those for a second. Let's move on to property L. Property L says that A transpose is an invertible matrix, and we saw in the last video that if A is invertible, then its transpose is also invertible. The properties A and L are also the same thing. So with the exception of J and K, we've gone through every single one of these properties, and we've seen that if one of them is true, all the other ones are true, right? So let's say we knew property B were true, then we could follow this trail from B to A to L to say, oh, L is true. We could follow this trail from B to C to D to E to F to say if B is true, then F is true, and so on. So what we've just shown is that if one of these properties is true, every single other one is true too. We can follow the path of the arrows. J and K are a little bit more nuanced, but not much, so let's give it a shot. If A is an invertible matrix, remember what that means. That means that there exists a matrix, let's call it A inverse, so that A times A inverse is the identity, and A inverse times A is the identity. So properties J and K each get half of this, right? So if A is invertible, then there certainly exists a matrix C so that CA is I. Specifically, A inverse could be that, right? So if A is invertible, it does indicate that that K is true, and it also indicates that J is true, right? Because that A inverse could be our C or our D. The problem is that we don't actually know, if we only know that, for instance, there's a matrix C, so that C times A equals I, we don't know that that same matrix could be multiplied on the other side to get us I, right? So we'll have to do a different method, because at this point, if we know A is true, all the rest of them are true. But if we know J is true, we don't actually know that any of the rest of these are true, because this arrow only points in one direction. So let's see if we can complete this out. We're going to try to do this by saying that J is going to imply D. So what this is saying is, if there's a matrix C, where C times A is the identity, we're going to try to show that that means that AX equals 0 has only the trivial solution. So if we look at AX equals 0, we want to show that the only solution to this is that X would have to be equal 0. So if AX equals 0, we're going to show that X has to equal 0. Well, we know that there's a matrix C, that when C times A are multiplied, that gives us the identity. So let's go ahead and multiply both sides by C. We have C times A times X and C times 0. Well, if we look at this side, anything times 0 is 0, right? So that one's easy. If we look at this side, we know from property J that C times A is the identity, and the identity times anything is itself, so we're left with X equals 0. That means that we have only the trivial solution. So property J implies property D. This is great news, because that means if we know J is true, then we know D is true, and if we know D is true, we know everything else is true. Success. All right, our last thing that we're going to try to do is we're going to match up K with G. So we're going to say property K implies property G. So again, now we're assuming there's a matrix so that A times D equals I. So again, the reason why we need to separate these out is because matrix multiplication is not necessarily commutative. All right, so we're trying to show that AX equals B has at least one solution for every B in Rn. So let's start by just picking a random vector in Rn. All right, and what we want to do is we want to find an X so that AX equals B. All right, so we're trying to find our X, but what do we know? all we know really is that A times D equals the identity, which is actually all we need to know. So if A times D equals the identity times anything equals itself, right? So this is the identity. So the identity times anything equals itself, but I could redistribute those parentheses and say this is the same thing as A times D times B equals B, and there it is. We have found our vector x. So we have found a solution to this A times x equals B, right? So to recap, we picked a random B and then we found an x that works for it. So K implies G. All right. So now that we have this diagram, we can see that for all of these 12 properties, if any single one of those properties is true, we can trace back all the rest of them are also true. And if any one of these is false, because the arrows go in both directions, so for instance, if C is false, then G has to be false, and if G is false, then H has to be false, and so on. The main takeaway here, if you didn't totally follow all those arrows, is that we have these 12 properties, and all of these 12 properties are either all true or all false. Our explanation for getting the diagram was just really diving into how are all these concepts that we've talked about all term related. Okay, now how can we actually use this? Let's maybe put our properties back up again. How can we actually use this? Well, basically what we would do to use this is, depending on what our question is asking us, we see, does it satisfy one of these properties, or does it specifically not satisfy one of these properties? Then all the other properties are either all true or all false. For each B and Rn, A transpose. All right, I think we mostly got everything put back again. So for example, if I gave you this matrix, 1, 2, 3, 1, 2, 3, 4, 5, 6. If I gave you this matrix right off the bat, we see that these two columns are the same. So that means what? That means that our columns are linearly dependent because we have two identical columns. So that means that this property, property E, is false because the columns aren't independent, they're dependent because our columns have repeats. That means every single other one of these is false. So we automatically know that, for instance, this matrix is an invertible. We automatically know that if we wanted to think of this as a linear transformation, it wouldn't be one-to-one or onto. We automatically know that the columns don't span Rn. We automatically know all of these things are false. Similarly, if we had something like I told you, okay, AX equals B, maybe I say this has multiple solutions. Maybe not for everything, but just for some B, for some vector B. This has multiple solutions for some vector B. What that means is that if I think of this as a linear transformation, that is not one-to-one. This is not one-to-one, this is false. So I automatically know, I don't even know what A is here. All I know is there are multiple solutions for some B, but since property F is false, all the rest of these are false. So even though I don't even know what A is, I know A isn't invertible. I know that the columns are linearly dependent. I know that this isn't an onto function. I know that its transpose isn't invertible right off the bat. If I, oh, yikes. Let's undo that. I'm back. Okay. I'm not going to erase that in case I erase the whole theorem. Okay. So let's do a new example. Now I don't know whether these are true or false. Let's say I had a new matrix. So I had A equals 1, 3, 4, 0, 7, 2, 0, 0, 5. Now if I look at this, I see, hey, look, if I kept on reducing this, there's a pivot in every single row and every single column. So specifically, in this case, property C is true. Without doing anything else to this matrix, I automatically know this matrix is invertible. this matrix, the columns are linearly independent. I know if it were a linear transformation, it would be one-to-one and onto. So this is how this invertible matrix theorem is incredibly, incredibly powerful, because without doing hardly any work at all, we can either identify one of these is true or one of these is false, and if one is true, all of them are true. If one is false, all of them are false. Great, so that's the invertible matrix theorem. That's all I have for you today. I will see you all in class.